Hello and welcome back, and if you are new here, welcome, we are very glad to have you here. Let us do just a quick recap of previous episode, where we talked about reference point. A reference point is agreed upon and set start value for taking measurements. We looked at example of altitude, and how and why sea level was declared as zero reference point for measuring altitude. We also saw what happens when we take negative measurement of some occurrence, and we also saw that in some cases, instead of insisting on formalism, like having negative altitude, we can use term depth and etc. Going forward in our goal to make a poor man's amplifier, we first have to take a close look at one of most common terms when dealing with electric circuits and electronic in general, and that is voltage. By definition, voltage is difference in potentials. But, what does that exactly mean? How can we visualize that difference and what is potential anyway? And why Earth has 0 volts? And what about Earth's electromagnetic field, what does it do, and what purpose does it serve? If Earth has electromagnetic field, and we know that when we move conductor through electromagnetic field, the current is being generated inside the conductor, then why can't we produce power in that way by just moving metal conductor through air, cheap and easy? In next episode we will deal with dogma, and current paradigm regarding current and electricity, but for now, let us just decide to believe that the current is directed and organized move of electrons through conductor, and that electrons that make current, flow from point with higher to point with lower potential. From elementary school physics we all know about experiment with electricity, rod, and fur cloth. If we rub rod with fur cloth, it gets charged and when we touch something metallic it sparks, or it makes our hair goes up when we pass the rod over our head. The other common experiment with electricity is a balloon that sticks to the ceiling when we rub our hair with it. In both cases we are taught that we charge the rod or the balloon with electricity by rubbing them with fur cloth or against our hair, and then after that at the surface of the rod and the balloon there are free electrons that stays there forever until we touch something metallic with them. In both cases the rod and balloon are considered negatively charged. So, how many volts are there on the surface of the balloon and rod? But, wait a minute. There are electrons there, and the current is made of electrons moving through the conductor. So, why aren't there 5 volts for me to charge my smartphone? First, these electrons are not moving. They will stay on the surface of the rod or the balloon until the end of time, or unless we discharge the rod or balloon by touching something that is grounded. Second, these electrons do not have a path to move. There are no conductors to make a path for them to flow. The air surrounding both balloon and rod is perfect isolator that prevents electrons jumping someplace else. Then, what purpose any of this serves? If electrons are going to stay there forever, then let them. They are useless. Not really. What those electrons have is potential. In this case you can visualize potential as a will to move to other place where there are not that many electrons. It's pretty crowded on the surface of rod and the balloon, so each electron wants to get free and loose, and go someplace else where there are not that many other electrons. So, their will and intent to go someplace else is called potential. The more electrons there are, their combined will and intent to go someplace else where there are not that many electrons is what makes a potential bigger, or more precisely higher. So, how do we measure how much a bunch of electrons is willing to go someplace else and how strong is their intent to do so? Obviously, there are many of them, and packed together on a small place their combined will is very strong. So, what happens to all those electrons when they spot an empty place where they can all go? What happens when we provide them with a path, A conductor, for example, to facilitate their journey to another place, they can call their forever home. Let's connect these two rods with a conductor, for example, a copper wire. Now we've made a path, a road for electrons to leave their previous home and journey to a new place they can call their new forever home. Let's see what happens now. What do you think? How many electrons will regret their decision to leave, and how many of them are going to go back? But wait a minute. This is the exact same situation as it was before. All electrons have moved, and they are as packed and as crowded as they were before, but just on another rod. This is wrong. Obviously, something is out of joint in here. What was the purpose of this lovely journey, if the situation is the same as it was before? Okay, let's calm down. Obviously, this is not what happens in real life. What we just saw would be a perfect example of perpetuum mobile, a never-ending motion. But, we all know that perpetuum mobile doesn't exist. The electrons cannot move from first to second rod indefinitely. No matter how strong is their will, and no matter how determined they are to find a new roomy home for themselves, they will eventually tire and settle. But, where? On the first, or on the second rod? And how many will decide to move, and how many will decide to stay? What will happen to their potential then? Let's skip journey animation this time and go to the point in time where first 4 of the electrons have moved to their new forever home. After their journey they are happy, they have more room and it is not as crowded as before. But, what about remaining 4 electrons from first rod? The situation is like this. After seeing exactly half of their brothers and sisters move to new place, they are content to stay on the same rod, because the number of electrons on second rod is exactly the same as the number of electrons on first rod. Nothing would be gained if 1 or more electrons move from one rod to another at this point in time. And, what is more important, they no longer have will or intent to move, because collective potential of all electrons on first rod is exactly the same as collective potential of all electrons on second rod. It doesn't matter anymore if there is a path for them to cross from one rod to another. Since the number of them is the same on both rods, nothing would be gained by moving, so they are happy to stay in this equilibrium forever. Given that our electrons have happily divided their numbers between rods, and there are exact same numbers of electrons on the first and on the second rod, we concluded that their combined collective will to move from one place to another is same, and they have decided that they are content to stay put. When we have the situation that 2 points in space, in this case 2 rods, have the exact same number of electrons on them, or to be more precise and exact, 2 points have the same amount of electric charge, we say that those 2 points have the same electric potential. What would happen if we introduce 2 or more rods, each one electrically charged in same way, each one containing the same number of electrons, and we cross-connect them with copper wire? Are there going to be any movement between rods? Are any of the electrons are going to journey from one rod to another? This time, there will be no movement of electrons between rods. Each and every one of the rods contain the exact same number of electrons, or to be more precise, each and every one of the rods is charged with the same amount of electrical charge. So, each rod, or to generalize our scenario, each point in space that is charged with same amount of electrical charge has the same potential. But is it enough to say only this? No. Our sentence is meaningless. To what value are we to compare the electrical charge of our rods? We need to introduce a reference point. In this point in time, we only have our 5 rods with same number of electrons sitting dormant on the surface of the rods. So, we can only compare them between themselves. In this point in time, we will say that each and every one of the rods have the same electrical potential in compared to all other rods, or to be more succinct, compared one to another, each has the same potential. From previous video, we have learned that this is called relative referencing, because we have no universal reference point, the one that contains universally set and agreed upon number of electrons, or set and agreed upon amount of electrical charge, or to be absolute, we do not have a zero potential reference point to compare the potential of our rods to. Time to introduce the planet called Earth. Now, we all know that Earth has a magnetic field that is ubiquitous. That internal magnetic field is what makes compass work. Now, from physics, we also know that magnetic field cannot exist on its own. It needs an electric field for company, and vice versa, electric field cannot exist on its own, it also needs a magnetic field for company, so these two seemingly different occurrences in nature are combined into one called an electromagnetic field. So, as a result, the Earth has an electromagnetic field that is ubiquitous. Next logical question is, if there are no electrons on Earth, where does that electromagnetic field comes from? Well, the truth is quite the opposite. The Earth contains endless number of electrons. So much, that we can take how many we want and put it on our rod or on our balloon, and it would make no difference at all in total number of electrons on Earth. Vice versa, we can take as many electrons from our electrically charged rod or balloon and put it back on Earth's surface, and it would not make difference at all in total number of electrons on Earth. If that number is so big, that there is nothing we can do to change it in any meaningful way, and it is fixed and set, universally accessible, then it makes a hell of a good reference point to be used in all our measurements and comparisons when dealing with electrical charges. Also remember, that in previous video we discussed using cumbersome large number for reference point. We saw that using big values makes it difficult to do the math, so whenever possible, we declare a zero value for reference point. Since Earth contains electrons in so vast number, that nothing we do can change that number in any meaningful way, we will go and declare that Earth has a zero electrical potential, and since we have declared that reference point is zero, we can now easily do the math and make all other computations. So, for the sake of our own convenience, Earth's electrical potential is zero for all applications and purposes. Let us go back now to our dormant electrons. But let us change a scenario just a little bit. Just for fun, let's electrically charge first rod with 8 electrons, and second with only 5. We know that electrons on first rod have a combined will and intent to go someplace else where there are no electrons at all, or at least is not as crowded as is on rod. The electrons on the second rod are just as the same. They also have a combined will and power to do exactly the same as their brothers and sisters on the first rod. They desperately want to go somewhere less crowded. But their numbers are not the same. There are more electrons on first rod, so their combined collective will must be just a little bit stronger than a combined will of those 5 on the second rod. We have named that will and intent as a potential. We can deduce that more electrons there are, stronger their combined will and intent is, so bigger the potential. To be precise, the electrical potential of first rod is directly proportional to the numbers of electrons residing on rod. More electrons there are, the bigger the potential. Let's mark that potential with letter V and index it with number 1, for first rod. Let us also do the same for second rod. We will mark the potential of second rod with letter V and index it with number 2. It doesn't matter what values V1 and V2 have, they can have whatever value you want to visualize, but what is important is, that V1 is greater than V2. Next, in what units are we measuring the electrical potential? In number of electrons? How much they weigh? Not really. The unit for measuring electrical potential is called volts, in tribute to smart man from Italy named Alessandro Volta who invented first battery. Now we are going to subtract V1 and V2. We will name the result we get as potential difference between rod 1 and rod 2. The name is befitting, since we are using subtraction between two values, it is natural that resulting value is called difference. Let's mark the result as delta V. In math, prefixing value with Greek sign delta usually marks result obtained by subtraction of two values. The abbreviation for volts is capital letter V, and by rules of writing equations it is enclosed in square brackets. Looking at the equation, there are simply too many letters V. From previous video we have learned that we can, for the sake of practicality, give other, more informal name to some occurrence we are measuring, thus avoiding cumbersome naming convention. To add more to the confusion, everything here is marked with letter V, both values taken, resulting value and SI unit volts used to note nature of values and result. Like in previous video where we renamed negative altitude to depth, we are going to do the same here. We will rename the result delta V from difference in potentials to new name, voltage. In essence, voltage is just more simple way to describe the result of subtracting values of two differently electrically charged points in space. And to make things more simple and easily readable, instead of delta V we will use letter U for voltage, and also to help differentiate it from letter V used in square brackets for SI measurement unit volts. So, our final equation for voltage becomes U for voltage is equal to potential difference V1 and V2, and it is measured in volts, written with letter V in square brackets. And that is voltage for you. From definition, we know that voltage is a difference in potential. How can we visualize voltage in order to make it more accessible and more understandable to us? Can we make an analog from known phenomenon to help us visualize and see voltage? Yes. You can visualize voltage as an invisible force that makes electrons move from place with higher potential to place with lower or zero potential. Simply put, voltage is that force that pushes electrons through conductor, for example, a copper wire, and that movement of electrons from place of higher potential to a place with lower or zero potential is called electrical current. So, there you have it. Now we know what potential is, we know why Earth has zero potential, we know what voltage is, and just for the sake of rounding things up, we have given a brief definition of current. Next, we will go more in details and explain how and why batteries work. All of us in our daily lives use batteries. From ones in smartphones, tablets, and laptops, ones we find in our TV remote controllers and other home electronics, to those we find in our modern electric cars. Despite the difference in their size, appearance, and scenario of usage, they all serve one purpose alone: to store electrical energy, which we later use to power our devices and cars. Now, we won't go in details how batteries are made, since there are too many types and varieties, that would take too much time. What we will do is explain, in simple terms, how all what was said in first part of this video relates to batteries, and what makes them work. One of the main characteristics of batteries is their voltage. Previously, we have learned that voltage is difference in potentials, and that means that in one part of battery there are too many electrons for their own comfort, and in the other part of battery there are none. Obviously, the more volts battery has, the bigger the difference in number of electrons in two parts of battery. Logically, 3.3 volt battery will have less electrons than 5 volt battery, and more than 1.5 volt battery. There are too many types of batteries and the manufacturing process drastically differs from type to type, so it would be impractical and tiresome to describe each and every one. In short, we will say that, during the manufacturing process, factory that makes batteries ensures that one part of the battery contains as many electrons as are needed to make potential difference of battery's desired voltage. This simplified schematic of inside of the battery will help us to make in and ends of internal mechanism of batteries in general. Please have in mind that this is not how real battery looks like inside, nor this is accurate depiction of inner works of batteries. During the manufacturing process, factory that makes batteries ensures that one end of battery has excess number of electrons. The factory will mark that end with plus. The other part of battery is marked with minus sign, and that part of battery is void of excess of electrons, it is empty. There is barrier between two parts, preventing electrons from spreading. From first part of this video, we know that overcrowded electrons desperately want to go to the place where is less crowded, but in this point in time, there is no path for them to move, there is no conductor, so they remain put. Let's introduce a light bulb, switch and a conductor that will provide path for electrons. Now, when we flip the switch, there is an open path for electrons to start their movement from overcrowded to less crowded place. Since electrons cannot traverse the barrier inside the battery, the shortest and easiest path for them to move is through the conductor and the light bulb, to their final destination, the empty part of battery. We have learned that voltage is that force that starts to push electrons to move through the conductor. We have learned, also, that exactly half of the electrons will move from plus side of battery, to minus side of battery. When their number in both parts of battery becomes the same, they will stay put. When the number of electrons in both part of the battery becomes the same, we say that battery is depleted. It doesn't matter that total number of electrons in battery remain the same, when there is no more movement in the circuit, we call that state depleted. In rechargeable batteries, process of pushing back all electrons to plus part of battery is called charging. During recharging process, stronger, or more precisely, bigger voltage from wall outlet pushes all electrons back to plus side of battery. That's how your phone's battery recharges over and over again. With the explanation of how batteries work, we conclude our story about potential, reference point, potential difference, voltage and batteries. In next video, we will give a quick introduction about electrical current. So, stay tuned for next video. Please, show your appreciation by liking this video, sharing it, leaving a comment, and consider subscribing. Thank you, and see you next time. Bye.